Invisible to the human eye, the hydrogen bridge drifts between galaxies like a phantom thread woven by the universe itself. Composed almost entirely of neutral hydrogen atoms, its density is so faint that in optical light it vanishes into the cosmic backdrop. Yet in the realm of radio waves, it becomes a structure of striking clarity, a filament stretching across intergalactic space, humming with the spectral fingerprint of the 21-centimeter line. This whispering nebula, as some theorists call it, is not a nebula in the traditional sense. It does not blaze with starbirth or shine with ionized brilliance. Instead, it is a structure of quiet potential, a bridge that links two massive galaxies across millions of light-years. The gas within it is cold, diffuse, and ancient, perhaps stripped during a gravitational interaction in the distant past, or formed through the tidal resonance of passing dark halos. Simulations suggest that such intergalactic hydrogen bridges may act as silent corridors for baryonic matter, funneling gas toward galactic disks and seeding the conditions for future stellar nurseries. At the same time, dark matter might drift through this tunnel, subtly shaped by its gravitational contours. While the luminous content of the bridge is minimal, its mass may be substantial when the invisible components are included. Observations using radio interferometers like ESCAP and MeerKAT reveal its fragmented texture, clumps and strands of gas, some rotating, others stretching outward in turbulent arcs. These structures may be transient, held together only briefly by a delicate balance of thermal pressure, turbulence, and gravitational inertia. But their existence suggests a dynamic universe in which even the voids between galaxies are not empty, but alive with complex flows and unseen architectures. High-resolution mapping of the hydrogen line intensity reveals intricate substructures within the bridge, some aligned with magnetic fields, others curving in patterns that imply past galactic flybys or minor mergers. Spectroscopic velocity profiles indicate that portions of the gas are moving coherently, as if tracing the memory of ancient gravitational tides. These flows may represent the residual pathways of cosmic migration, where matter was siphoned from one galactic halo into another during encounters billions of years ago. Recent studies using stacking techniques and cross-correlating deep-field radio surveys with optical redshift catalogs have uncovered dozens of similar hydrogen filaments across cosmic time. They are faint, elusive, but surprisingly common. Some span over 500,000 light-years, connecting dwarf galaxies, others stretch between spirals on the brink of merging. In nearly every case, the filament carries not only gas but a subtle velocity shear, a telltale signature that it is not static, but evolving. One of the key questions under investigation is whether such bridges contribute to the replenishment of galactic gas reservoirs. In the cold dark void where few new materials are expected to appear, these bridges may provide a lifeline for galaxies that would otherwise starve and fade. In the Lambda CDM framework, simulations like Illustris TNG and Eagle suggest that up to 10% of a galaxy's gas mass over cosmological timescales might come from low-density intergalactic streams, most of them invisible without radio detection. The role of magnetic fields is another frontier. Polarization measurements show weak, coherent signals along some of these bridges, implying that magnetohydrodynamic forces may help maintain their structure against dispersal. This opens new paths in understanding how cosmic magnetism shapes not just galaxies and clusters, but also the connective tissue between them. Researchers are now turning to next-generation radio telescopes like the Square Kilometre Array, SKA, which promise unprecedented sensitivity to diffuse, low-brightness emission across vast cosmic volumes. With its ability to detect hydrogen signals at redshifts previously unreachable, the SKA may reveal whether these bridges were more common in the early universe, possibly tracing the primordial scaffolding of the cosmic web before galaxies had fully coalesced. Intriguingly, some models propose that these hydrogen bridges are not merely passive remnants but active channels for feedback. Supernova-driven winds or AGN outflows from the host galaxies could inject energy into the bridge, creating shock fronts or even triggering localized collapse within dense knots of gas. This raises the possibility that stars, albeit rare, could form directly within the bridge, suspended in intergalactic space, far from any galaxy's center of gravity. If confirmed, such phenomena would challenge classical definitions of stellar environments and broaden our understanding of where, and how, stars can be born. It would mean that the gravitational boundary of a galaxy is not the true limit of its influence. Its reach may extend far beyond its visible disk, shaping and seeding regions across hundreds of thousands of light-years. Some bridges show asymmetries in chemical composition, with trace amounts of carbon, oxygen, or sulfur unevenly distributed across their length. This suggests a mixed origin, some gas stripped from enriched galactic outskirts, some drawn from more pristine, intergalactic reserves. The metallicity gradients hint at a slow alchemy taking place, cosmic material being stirred, stretched, and diluted across eons, perhaps preparing raw ingredients for future stellar generations. As detection techniques become more refined, scientists are beginning to suspect that these hydrogen bridges may be far more than passive structures. Some theorists propose they are dynamic regulators, balancing the inflow and outflow of matter between galaxies, synchronizing their evolution like unseen cosmic umbilicals. These bridges could form a kind of galactic circulatory system, slowly exchanging energy, angular momentum, even magnetic topology between once isolated systems. It's even been hypothesized that these structures could serve as highways not only for matter, but for information, waves of radiation, turbulence, or magnetic pulses transmitting signals of galactic activity across millions of light-years. In that context, the whispering nebula takes on a poetic resonance, a silent messenger, conveying whispers of starbursts, black hole outbursts, and gravitational perturbations from one realm to another. More intriguingly, some researchers are exploring whether these bridges could amplify or sustain exotic phenomena. In simulations, under certain density and magnetic conditions, hydrogen filaments can support plasma instabilities that resemble natural waveguides, conduits for relativistic particles or even low-frequency electromagnetic waves. If verified observationally, this could mean that hydrogen bridges are not only shaped by galaxy interactions, but may participate in a deeper astrophysical feedback loop, influencing the environment between galaxies in real time. One especially tantalizing clue comes from recent Faraday rotation studies. As radio waves from background quasars pass through these bridges, their polarization subtly twists. This indicates the presence of weak, coherent magnetic fields threading the structure, perhaps remnants of ancient cosmic dynamos, or filaments inherited from early universe turbulence. These fields, while faint, could influence the dynamics of baryons and even interact with the large-scale structure of dark matter. Some cosmologists propose that such bridges might align along hidden filaments of the cosmic web, acting as luminous signposts for the underlying dark matter skeleton. Since dark matter doesn't emit or absorb light, its presence must be inferred through gravitational influence, but if hydrogen bridges preferentially form along its contours, they could offer a new kind of tracer, the ghostly breath of an invisible architecture. If this hypothesis holds true, then each hydrogen bridge becomes not just a thread of gas, but a revelation. A glowing imprint of gravitational tension drawn across the void, whispering the outlines of dark matter's invisible hand. We might be witnessing a form of intergalactic archaeology, fossilized remnants of cosmic interactions, stretched and frozen across eons, preserving the dynamics of past collisions like ripples on a vast, multidimensional ocean. Even their geometry hints at deeper patterns. Some bridges appear curved, looping like tendrils toward their galactic hosts, others stretch taut and linear, resembling stretched membranes under tension. In a few rare cases, they fork, branching into Y-shaped structures whose symmetry defies random formation. These geometries are being compared to models from string theory and fluid dynamics, as if the same physical laws that govern the microcosm are at play in the largest voids of space. But perhaps the most provocative mystery lies in their temporal evolution. Are these bridges transient flickers in cosmic time, ephemeral connections that unravel in a few 100 million years, or could some endure for billions, surviving as stable conduits through galactic epochs? If they persist, might they evolve? Might they accumulate enough mass to birth dwarf galaxies within themselves, turning from passive corridors into active progenitors of cosmic structure? Already, hints of such transformation have been seen. In one bridge between two interacting spirals, astronomers detected compact knots with rising velocity dispersions and slight infrared excess, potential signatures of cold collapse and nascent star formation. If confirmed, this would mean stars are being born in the void itself, nurtured not in disks, but in the whisper-thin strands of a hydrogen thread stretching between worlds. And beyond that? Some theorists have speculated that dark matter, if it is weakly interacting yet responsive to gravitational shaping, might use these bridges as preferred paths, low-energy routes through the gravitational landscape, threading through minima in the cosmic potential field. If such a dark flow exists, then these bridges may not only mark gravitational scars, they may channel the very lifeblood of the universe's large-scale evolution. In this vision, the hydrogen bridge is not merely a residue of past encounters but a key actor in a cosmic choreography, an unseen arterial system through which both ordinary and dark matter circulate, shaping the destiny of galaxies. It invites a rethinking of what defines a galactic environment. Where does a galaxy end, if its influence bleeds into intergalactic space along filaments of gas, magnetism, and memory? These structures blur the boundary between galaxy and void, challenging the very notion of isolation in the cosmos. No galaxy, it seems, evolves entirely alone. Even across gulfs of darkness, there exist threads of relation, kinetic, chemical, gravitational. The whispering nebula is one such thread, its voice inaudible to us but resonant in radio, in magnetism, in curvature of spacetime itself. And as our instruments sharpen, we may soon be able to decode this voice. Next-generation spectroscopic arrays promise to map velocity fields within bridges with exquisite precision, revealing turbulence, compression waves, and potential signs of gravitational collapse. Combined with X-ray and infrared data, we might detect faint emissions from warm gas pockets, evidence of past supernova shocks or tidal heating as galaxies pull on their tethered neighbors. If these bridges indeed seed future galaxies or host isolated bursts of star formation, they may offer insight into how structure forms outside the canonical bounds of dark matter halos. This opens a window onto early cosmological epochs when the first filaments condensed out of the quantum haze of the primordial universe. Perhaps today's hydrogen bridges are echoes of that first assembly, cosmic strings redrawn in softer, colder matter. And at their heart may lie more than gas. Some researchers speculate that intermediate-mass black holes could wander along these filaments, unanchored to galaxies, feeding slowly on the rarefied medium. Others suggest that axion-like particles, hypothetical dark matter candidates, might convert into detectable photons in the magnetic fields of such bridges, a process that could finally illuminate the nature of dark matter itself. In this way, the whispering nebula becomes a laboratory not only for astrophysics, but for fundamental physics. A liminal place where baryons, dark matter, magnetic fields, and possibly new particles converge in complex, elegant flows. Such liminal zones, neither fully galactic nor entirely void, may be the universe's most subtle but revealing frontiers. In these diffuse regions, physical laws express themselves with nuance. Gravity acts gently, magnetism stretches thin, turbulence dances in slow motion. Here, the universe is not loud and explosive, as in the heart of a quasar or the chaos of a supernova. It is quiet, deliberate, and whispering in long wavelengths. Yet the questions it raises are among the most profound. What governs the coherence of these bridges across such vast scales? Why do they persist against entropy, resisting dissipation despite their fragility? Could there be an underlying topology to spacetime itself, one that naturally encourages filamentary structure not just in matter, but in the very fabric of the quantum vacuum? Some physicists propose that quantum fluctuations in early inflation seeded these patterns, which later gravitationally amplified into the vast web we see today. If so, hydrogen bridges are not just links between galaxies, They are fossilized expressions of the universe's birth tremors. From this perspective, studying these bridges becomes an act of deep cosmological archaeology. Every spectral line, every polarization angle, every twist of velocity is a brushstroke on the ancient canvas of cosmic history. And just as fossils on Earth tell us how life evolved, these intergalactic strands may reveal how galaxies, clusters, and perhaps even the rules of structure formation emerged. The philosophical implications are equally stunning. If the void is not void, if even emptiness holds memory and motion, then isolation is a myth. The universe is fundamentally connected, not in a metaphorical sense, but physically, through real tendrils of gas and field that braid space and time together. Galaxies do not merely drift through darkness, they are immersed in a shared, dynamic medium, shaped by tides and echoes that flow across the cosmos. In this shared medium, the whispering nebula becomes not just a scientific curiosity but a symbol of interdependence. A structure so delicate it vanishes in visible light, yet so fundamental it may orchestrate the evolution of entire galactic ecosystems. We are only beginning to understand it. And yet, in every frequency we tune, in every redshift we scan, the whispers grow louder. What, then, are these whispers telling us? They speak of a universe far more intricate and symphonic than the stark void once imagined. They murmur of pathways not charted by stars but by invisible flows, gas currents, magnetic filaments, gravitational tremors that stretch across megaparsecs. They hint at coherence across chaos, at structure rising from seeming disorder, at faint rhythms that pulse through the deepest dark. In some regions of these bridges, the hydrogen appears partially ionized, not enough to glow in optical bands, but enough to suggest past exposure to ultraviolet radiation. Could this be the faded echo of a quasar flare long since extinguished, its photons having bathed the bridge and altered its state? Or perhaps these filaments occasionally light up with transient events, cosmic lightning strikes that briefly illuminate their span before fading once more into stillness. There's also growing speculation that these intergalactic tendrils may house exotic forms of turbulence, slow, large-scale analogues of what we see in planetary atmospheres or stellar convection zones. In such an environment, the Reynolds numbers are vast, and the inertial cascades could take millions of years to unfold. Turbulent eddies within the bridge might gather and concentrate gas over millennia, creating seeds for dwarf galaxies or isolated star clusters. These, bridge-borne, systems would represent a new class of cosmic object, offspring of gravitational dialogue, born between worlds. Future observatories, particularly in the far-infrared and low-frequency radio regimes, may detect the faint heat signatures of such embryonic structures. And if they do, it will confirm that bridges are not only scars, not only echoes, but wombs, cradles suspended in the vastness, quietly forming new chapters of cosmic evolution. And perhaps the most haunting idea of all, that somewhere along one of these bridges, in a knot dense enough to briefly ignite nuclear fusion, a star may have formed, and around that star, a planet. And on that planet, chemistry. And within that chemistry, the slow-burning possibility of life. Not tethered to a galaxy. Not nurtured by a grand spiral or elliptical host. But born in the between. In the whisper. In the silence between empires of light. Such a possibility reshapes our understanding of where life could emerge, not merely within the protective cocoons of galactic habitable zones, but far beyond, in the liminal space where gravity weakens and light thins. A single rocky world orbiting a bridge-borne star could drift for billions of years in intergalactic solitude, shielded from violent starbursts, untroubled by galactic collisions, basking in the faint warmth of a stable red dwarf. Its sky would not be filled with constellations, but with an abyss, punctuated by the distant shimmer of galaxies, like lanterns hung across a cold, eternal sea. Could intelligence arise there? Could consciousness bloom in such isolation, born not of stellar abundance but of silence, reflection, and time? Would such beings, if they evolved, even know what a galaxy is? Would they look outward and see their bridge as the entirety of reality, an endless, delicate river of gas, occasionally pulsing with the light of far-off galaxies, never realizing they float within a grander cosmic web? It forces us to ask, what is the minimum requirement for life? A star? A rock? Or simply time, matter, and a quiet place to think? The whispering nebula may offer all three. In its stillness, in its invisibility to our eyes, it may host the rarest kind of existence, one not defined by galactic drama, but by intergalactic persistence. And for astronomers today, these bridges represent a threshold. To study them is to study what binds the universe, not just in mass and momentum, but in narrative. They are the in-between spaces where histories of galaxies converge, where dark matter sculpts silent paths, where the aftershocks of ancient collisions still echo. Every filament, every gradient, every twist and polarization carries the imprint of forces we barely understand. It may be that in the end, these hydrogen bridges are the closest thing we have to cosmic handwriting. Not declarations of power, like quasars or gamma-ray bursts, but subtle, enduring scripts, written across space in the ink of atoms, revealing the quiet grammar of structure, connection, and transformation. To read them is to begin decoding the language of the universe itself. And the deeper we read, the more the universe begins to resemble a living manuscript, its pages woven not of paper and ink, but of filaments and forces, hydrogen and silence. Each bridge is a sentence suspended between galaxies, each fluctuation in density a punctuation mark shaped by gravity's hand. The whispering nebula is not an object, it is a phrase in an unfolding conversation that began billions of years ago and has never ceased. With each new observation, with each spectral line decoded, we trace the syntax of cosmic connection. There is an elegance here that rivals any cathedral of stars, a structure so tenuous it seems it should not exist, yet so persistent it defies the chaos of time. In the language of astrophysics, it is a low-density intergalactic filament. In the language of wonder, it is a breath drawn across the abyss. And perhaps that is its greatest gift to us, not simply what it reveals, but what it invites us to imagine. These bridges remind us that the universe is not a disjointed scatter of islands but a woven continuum. That between every two things, there is a third, a relation, a memory, a thread. The galaxies at either end may shine with grandeur, but it is the bridge between them that tells the deeper story, the quiet story, the connective story. And this whisper is growing louder. With next-generation instruments poised to illuminate the darkest corners of the cosmos, we may soon map not just the bridges themselves, but the subtle forces flowing through them, thermal winds, magnetic undulations, quantum relics of the early universe. We may detect new elements within these filaments, or signs of prebiotic chemistry, or long-cooled embers of primordial stars. One day, the whisper may reveal an echo of the first light, the afterglow of cosmic dawn not captured in the usual maps of reionization, but refracted softly through hydrogen strands stretched thin by time. Or perhaps we will find evidence of something stranger, gravitational wave patterns localized within bridges, suggesting they may resonate like strings under cosmic tension, trembling in harmony with the unseen architecture of the quantum vacuum. In that trembling, faint, vast, and ancient, we may finally glimpse the bridge not only between galaxies, but between physics and meaning. Already, observational campaigns are pushing into this frontier. Instruments like LOFAR, low-frequency array, CHIME, and the upgraded VLA are beginning to capture extended hydrogen emission beyond the bounds of known galaxies. Using deep integration and refined foreground subtraction, researchers have detected spectral anomalies, faint, elongated features consistent with intergalactic bridges extending over hundreds of kiloparsecs. These are not incidental clouds or random overdensities, they exhibit continuity, velocity coherence, and alignment with large-scale gravitational flows. In particular, HI mapping surveys have revealed bridges with consistent Doppler shifts, suggesting bulk motion of gas along their length. Some bridges show signs of shearing, a differential flow where one side of the filament moves faster than the other, possibly due to tidal interaction or gravitational torque from orbiting galaxies. These velocity gradients provide a unique laboratory for studying the dynamics of baryonic matter under extremely low pressure, low temperature conditions, regimes nearly impossible to replicate on Earth. Meanwhile, numerical simulations have caught up with the observations. High-resolution cosmological models, such as those from the FIRE and Illustris TNG projects, have begun to reproduce bridge-like structures as natural byproducts of galaxy interactions and cosmic web evolution. In these simulations, bridges form not only during collisions but also via filamentary accretion, cold flows of hydrogen gas streaming along dark matter veins, feeding galaxies while leaving behind residual traces. These simulated bridges exhibit turbulence, mixing layers, and even shock fronts, all of which are now being sought in real data. A particularly exciting development involves the integration of machine learning into bridge detection. Deep neural networks trained on simulation data are now being deployed across massive radio sky surveys, scanning for subtle signals that might elude classical detection thresholds. These systems are already identifying candidate bridges previously missed, suggesting that the population of hydrogen filaments may be far more numerous than we imagined. And with new missions on the horizon, such as the SKA, the Nancy Grace Roman Space Telescope, and advanced ALMA upgrades, astronomers expect to soon probe not only the structure of these bridges, but their thermodynamics, ionization states, and elemental compositions. Spectropolarimetric analysis will help disentangle the tangled magnetic geometries within the bridges, revealing whether large-scale magnetization is a relic of galaxy-scale dynamos or a primordial cosmic web feature. Each of these lines of inquiry converges on a single, profound truth: intergalactic bridges are not accidents. They are structural, persistent, and perhaps essential. Their persistence across time and scale hints at something deeper, an embedded architecture within the universe, one that does not just permit bridges to form, but prefers it. This preference is not anthropic, but physical, a consequence of gravity, thermodynamics, and the initial conditions of the universe itself. In the Lambda CDM framework, the large-scale structure of the cosmos emerges from primordial quantum fluctuations that were stretched during inflation. As these fluctuations collapsed under gravity, they formed a cosmic web, a vast interconnected lattice of dark matter filaments. Along these filaments, baryonic matter, ordinary gas, flowed like sediment in a gravitational river, cooling, condensing, and giving rise to galaxies where the knots converged. But between those knots, much of the gas never formed stars. Instead, it remained suspended, faint, cold, and whispering. These are the hydrogen bridges we now glimpse. Their mere existence confirms predictions made decades ago but never observed until recently. And they fill in a critical gap, the missing baryon problem. For years, astronomers knew that a significant fraction, perhaps 30–40%, of the ordinary matter predicted by Big Bang nucleosynthesis was unaccounted for. It wasn't in stars. It wasn't in galaxies. And it wasn't in hot intergalactic gas visible to X-rays. But slowly, through sensitive radio and UV absorption line observations, that matter has been found, not clumped into galaxies, but stretched out in bridges. Some exists as diffuse, warm, hot intergalactic medium, WIM, but a growing share is being identified as cold neutral hydrogen, CHI, within these filamentary structures. And the more we observe, the more we realize that galaxies are not isolated systems, but condensations within a vast, fluid continuum of gas and dark matter. The temperature and ionization structure of these bridges vary widely. In some cases, far UV spectroscopy with instruments like HST's Cosmic Origin spectrograph has revealed traces of doubly ionized oxygen, O6, indicating regions of gas at hundreds of thousands of degrees Kelvin, likely shock-heated by interactions or galactic outflows. In others, the gas remains cool and neutral, detectable only via its hyperfine 21 cm emission line. What's particularly fascinating is that some bridges appear to light up only temporarily. Time domain surveys suggest that galactic outbursts, like quasar episodes or supernovae, can send radiation waves propagating through the bridge, briefly ionizing it or altering its molecular chemistry. These episodes, although rare, act as diagnostic tools, allowing astronomers to measure density, metallicity, and response time of gas many kiloparsecs away from any star-forming region. Moreover, the morphology of these bridges, some straight, others warped, spiraled, or even bifurcated, offers insight into the gravitational environment through which they stretch. A bridge that curves, for instance, may indicate the presence of an unseen satellite galaxy or dark subhalo perturbing its trajectory. Thus, these structures are not only archives of past galactic interactions, they are also gravitational seismographs, recording the tremors of nearby invisible masses. Perhaps most tantalizing are the chemical fingerprints encoded within them. Some bridges contain regions enriched in heavy elements, carbon, nitrogen, iron, dispersed unevenly across their length. These metals are clues, pointing to past stellar death and outflows. But they also suggest a kind of intergalactic recycling, that elements forged in one galaxy can, via bridges, drift for hundreds of thousands of light-years before falling into another, seeding its future generations of stars and planets. A cosmic exchange. A galactic ecology. And in this ecology, bridges may even serve a regulatory role. If they channel gas from the intergalactic medium back into galaxies, they could help stabilize or restart star formation in galaxies approaching quiescence. Conversely, they may carry away enriched gas, cooling feedback loops and preventing runaway growth. This makes them not passive links, but active agents in galactic metabolism. In that light, the Whispering Nebula becomes something even more extraordinary, a living system at intergalactic scale. Delicate, nearly invisible, but essential, quietly shaping the life cycles of galaxies, regulating the flow of matter and information, binding the universe not just gravitationally, but evolutionarily. And we are only beginning to hear its voice. As we tune our instruments ever finer, the voice of the Whispering Nebula becomes more structured, no longer a vague murmur, but a chorus of data, line profiles, polarization signatures, metallicity ratios, velocity dispersions. Each of these is a syllable in the deeper language of the cosmos, and together, they compose a grammar of intergalactic interaction. New observational programs are focusing on what happens at the termini of these bridges, how gas enters or exits galactic halos. The interface between a hydrogen bridge and a galaxy's circumgalactic medium, CGM, is a turbulent frontier, where inflowing cold gas meets the hot, enriched atmosphere surrounding the host. In some systems, this boundary sparks Kelvin, Helmholtz instabilities, turbulent mixing layers where velocity shears drive vortices, entraining cold gas into the hot medium or vice versa. These regions are now being studied through Lyman alpha absorption lines and high-resolution simulations. Meanwhile, in low-mass galaxies and groups, the bridges may serve as dominant modes of gas accretion. Without deep gravitational wells or strong feedback mechanisms, these galaxies can't rely on mergers or cooling flows from hot halos. Instead, they sip from the filaments, slow, steady accretion from bridges that keep star formation alive across gigayears. This process, known as cold mode accretion, may explain how dwarf galaxies maintain activity in otherwise sparse environments. Interestingly, some bridges exhibit a kind of asymmetry, not just in structure, but in time. One side may show recent star formation or chemical enrichment, while the other remains pristine. This suggests a directional history. The bridge may have formed in a one-sided tidal event, or through asymmetric stripping during a high-speed galactic encounter. Studying these time asymmetric bridges can help reconstruct the dynamic history of galaxies across cosmic time, like reading the wake of a ship long vanished from view. And beyond the baryonic gas lies the enigma of dark matter. Although invisible, its presence is inferred through gravitational lensing and dynamical modeling. Some bridges are thought to trace dark filaments, thin extensions of massive halos whose presence can only be deduced by the shape and behavior of the luminous matter they influence. When a hydrogen bridge aligns with a gravitational lensing arc or a galaxy cluster's X-ray contour, it suggests a coupling between luminous and dark matter components, a ghostly scaffolding around which gas condenses. This has led to a radical idea, that hydrogen bridges may be the observable surface of a deeper, hidden structure, dark filament, threading the cosmic web. If this is true, then every detection of neutral hydrogen between galaxies is not just a discovery of gas, but a detection of shape, of form, of presence where none was expected. The void is no longer void. It has structure. It has history. It has voice. And that voice, faint, scattered, refracted through gravity and plasma, is a message from the early universe. It tells us that the story of galaxies is not written in isolation. It is braided through the threads that connect them. That what falls into a galaxy today may have drifted across 500,000 light-years to get there. That the iron in a newborn star may have once belonged to the corpse of a long-dead supernova in another spiral. That the future of one galaxy may depend on the quiet persistence of a bridge born billions of years ago, still whispering across the dark. These bridges, then, are not remnants, they are process. Not scars of ancient collisions, but living, evolving systems etched into the fabric of spacetime. They record not just the past, but actively mediate the future of galaxies. Every atom in these filaments is in transit, a messenger, a seed, a thread in the continual weaving of cosmic structure. In this sense, the Whispering Nebula is a transitional realm, a liminal zone where matter is neither bound nor free, neither in a galaxy nor in the void. It challenges our classifications. In the traditional cosmic census, matter is divided into stars, gas, galaxies, and intergalactic medium. But hydrogen bridges ignore these borders. They are threads in between, slipping through the definitions we once thought firm. This ambiguity is their strength. It allows them to act as mediators between scales, from the galactic to the cosmic. In large-scale structure simulations, when researchers include the impact of feedback, galactic winds, AGN jets, supernovae, they find that matter is not simply ejected into space and lost. Instead, much of it flows along pre-existing paths, it bends, it swirls, it is recaptured. The bridges guide this flow, like vascular systems distributing nutrients and waste in an organism. The universe, in this view, becomes almost metabolic. And if galaxies are organs in this cosmic body, then bridges are the arteries. They carry gas that will become stars, stars that will make elements, elements that will form planets, and perhaps life. They transport entropy, angular momentum, even magnetic helicity. In doing so, they regulate more than material balance, they sculpt possibility. This is why the next frontier in astrophysics is not the core of the brightest quasar or the heart of the densest cluster. It is the faint thread stretched between them. There, in that cold, low-density medium, we will find clues not just to how galaxies grow, but to how the universe functions, as a connected, evolving, information-rich system. Indeed, recent proposals suggest that even gravitational waves, ripples in spacetime from the merger of black holes, could leave subtle, transient signatures in these bridges. A passing wave could compress or stretch a filament just enough to alter its density or velocity field, potentially detectable with ultrasensitive surveys. In this scenario, the bridge becomes not only a structure of gas, but a detector, a cosmic seismograph feeling the deep tremors of the universe. And further still lies the question of origin. If bridges predate the galaxies they connect, if they are fossil filaments from the cosmic web's earliest scaffolding, then their study may unveil physics beyond the standard model. Some theorists speculate that the topology of these structures could hold signatures of exotic phenomena, cosmic strings, axion fields, or anisotropies imprinted during inflation. In this sense, the hydrogen bridge is not merely astrophysical, it is cosmological. A remnant of the initial conditions. A tracer of invisible architecture. A quiet map of the vast, interconnected machinery behind all things bright and burning.